Astonishing things that we would never have envisioned will be uncovered to us. Is this the sort of group where everything appears possible? We will find mind-boggling things that we never envisioned. And isn't that typical of this group where the unthinkable comes? Potential individuals have frequently addressed whether they are the only species in the wide universe. We have investigated the possibility of life beyond our little blue planet, gazed at the sky, and contemplated far-off cosmic systems. Finally, that chance has appeared. The head of NASA has recently said that something astounding has been caught by the James Webb Space Telescope, our window to the universe. Set yourself up for a mind-blowing secret that has been uncovered on the edges of our astronomical sector, the discovery of life on the planet Proxima B. This discovery adjusts everything as we investigate the secrets uncovered by the James Webb Telescope and hypothesize on the potential ramifications of finding life on Proxima B for both mankind as a whole and space exploration overall. A scientific wonder, the James Webb Space Telescope has the potential to completely change how we understand the universe. Because of the telescope's cutting-edge technology and extraordinary position in space, researchers can now study far-off worlds, planets, and stars in a way that has never been possible, giving them an unmatched perspective of the universe. Although all of this seems like a lot of cheesy statements, the technology genuinely supports all of that. The 6.5-meter diameter primary mirror of the JWST is one of its most astounding features. This is over 2 times as large as the primary mirror on the Hubble Space Telescope, quite possibly one of the most significant space exploration instruments of the last 30 years. The JWST's huge mirror allows it to capture even the smallest light flickers from the farthest reaches of the universe, regions that science hasn't forever been able to notice. Hence, for most of the time since forever ago, researchers have only made hypotheses about what is possible to see using a traditional telescope. However, with this one, they can finally see the genuine details of which they had been fantasizing. The JWST has a big mirror in addition to an assortment of cutting-edge instruments that can detect a wide range of light frequencies. The telescope's near-infrared camera, or NIRCam, as it's usually known, is a powerful instrument designed to take pictures in the near-infrared part of the electromagnetic spectrum. Why does this matter? Well, we can go further into the depths of the universe because near-infrared light can pass through dust clouds that block out visible light. Astronomers can see the formation of stars and planets up close, thanks to NIRCam's high-resolution imaging capabilities. The main objectives of this specific equipment are to investigate the early universe and its most memorable light, look into the beginning and development of galaxies, and find and describe exoplanets previously inaccessible by telescopes. Hidden complexities and structures are uncovered in the detailed photographs taken by NIRCam. Grasping the gathering and development of galaxies over time is supported by this, and it provides insights into the complex processes that shape our vast area, and then some. Anyway, that is just one instrument. The near-infrared spectrograph, or NIR-SPEC, is another option. Through the process of breaking down the light emitted by astronomical objects into its constituent tones or frequencies, it raises present expectations for the investigation of stars and galaxies. This technique, known as spectroscopy, provides significant details about the temperature, speed, and chemical composition of these objects. NIR-SPEC gives researchers detailed information about all that it observes. Thanks to its ability to study the spectral signatures of stars and galaxies, by analyzing the spectra's absorption and emission lines, researchers can identify the components of a star or galaxy and learn about the materials that make up the universe. This information helps in our understanding of the complex interactions that occur among stars and galaxies, as well as the life cycles of these celestial bodies. Besides, NIR-SPEC is essential for studying distant high-redshift galaxies. These galaxies emit light that has taken billions of years to reach us, giving us insights into the early universe. Astronomers might determine a galaxy's age, chemical composition, and other properties by examining its spectrum, which provides understanding into the galaxy's entire transformative history throughout astronomical history. The mid-infrared instrument, or MIRI, on the JWST is the principal instrument for investigating the mid-infrared portion of the electromagnetic spectrum. With MIRI, we can study objects that produce infrared light at longer wavelengths, allowing us to investigate a variety of phenomena, ranging from star formation to the discovery of exoplanet atmospheres. Investigating the dusty conditions where stars are formed is one of MIRI's primary goals. These dense dust clouds are permeable to infrared radiation, which enables MIRI to look through the astronomical cover and observe the formation of stars and planetary systems. Astronomers may learn a great deal about the actual processes taking place within these stellar nurseries, thanks to the detailed photographs and spectra it captures in the mid-infrared. That's not all, though. In addition, MIRI is essential for the identification and analysis of exoplanets. It enables MIRI to detect and examine the faint thermal emissions from exoplanet atmospheres. It achieves this by making mid-infrared observations. The composition, temperature, and movement of exoplanets, as well as their potential habitability, might be examined due to this capability. We can identify the presence of water vapor, carbon dioxide, and other essential chemicals thanks to MIRI's discoveries, which might indicate the fundamentals for life as we know it. However, those are just components that could support life. How does the James Webb Telescope look for biological markers? Spectroscopy and atmospheric analysis, which utilize the four instruments we just discussed, are two of its essential techniques. You see, a planet might not have had plants or oxygen from the outset, even while those show life to us. Science doesn't consider that to be the groundwork of life on a planet. Therefore, the telescope needs to become very precise. Spectroscopy, a method that lets researchers look at light produced or consumed by an object to determine its composition, is at the core of this strategy. Spectroscopy plays a significant role in revealing the molecular secrets hidden in the atmospheres of exoplanets. When the JWST observes an exoplanet, it anticipates a transit event, which is a celestial display in which the exoplanet appears to us as it passes in front of its home star. During this transit, the JWST closely monitors the starlight passing through the exoplanet's atmosphere with its state-of-the-art instruments. The JWST records this cosmic light while MIRI dominates the mid-infrared range and NRSpec focuses on the near-infrared. When combined, they form a powerful team that can cover a broad array of frequencies required for in-depth analysis. What exactly is the significance of gathering starlight during a transit, one might wonder. This starlight contains significant information on the composition of the exoplanet's atmosphere. Light interacts with various chemicals in the exoplanet's atmosphere as it passes through it, leaving behind traces like atomic fingerprints on the cosmic material. After that, the JWST begins its meticulous examination of the light it has captured by investigating the absorption or emission lines in the light spectrum. Researchers can utilize the telescope's spectroscopic capabilities to pinpoint specific mixtures that are present in the exoplanet's atmosphere. Since each molecule has a unique set of spectral characteristics, no two atoms will be the same. To bring the whole tale to a single lucid page, they basically have to be inspected and gathered to acquire exact discoveries. The JWST does complete modeling and calibration. It matches the observed spectral features with their corresponding chemical identities, utilizing complex programmatic insights and reference spectra of known substances. Consider it as a sort of cross-referencing a galactic dictionary to understand the atmospheric language of the exoplanet. Compounds are just the most important phase in the search for life, and all the more comprehensive procedure is required. Analysts search for particles that are viewed as biomarkers or mixtures that may be associated with life as far as we might be concerned. As we've referenced beforehand, these biomarkers may comprise gases that are vital for life on Earth to exist. For example, oxygen, methane, and water vapor. All things being equal, more data and observations are expected to assess the general tenability and any applicable organic movement pointers. Similar spectroscopy is one more instrument that the James Webb Space Telescope, JWST, uses to work on its chase after life. To draw significant correlations, researchers look at a couple of exoplanets with practically identical properties instead of a huge number of confined exoplanets. Tracking down repeating patterns or variations in the observed spectra of different exoplanets is the objective of similar spectroscopy. By examining a range of exoplanets, some of which might be tenable while others may not, we can search for examples or oddities that could reveal insight into the presence of atoms or cycles pertinent to life. The JWST looks for exoplanets that are tantamount to one another in terms of size, mass, separation from their host star, and other relevant factors to conduct similar spectroscopy. Thus, scientists can isolate the effects of various environmental parts and focus on conceivable livability pointers. Researchers can look for similarities or contrasts in the distinguished synthetic absorption or discharge lines by contrasting the spectral data gathered from these objective exoplanets. It could be an indication that fundamental parts of life, such as oxygen, methane, or water vapor, are available on potentially habitable exoplanets if explicit mixtures or examples are consistently observed in their spectra. The context that the correlation method offers is very useful in figuring out the spectroscopic information. It empowers analysts to observe between attributes that are bound to be connected to life and those that could be credited to non-organic peculiarities like volcanic activity or environmental science. This is because, notwithstanding giving off an impression of being restricted to Earth, peculiarities like volcanic movement in reality happen across space. Despite the fact that a few planets are very much unfriendly, they experience incredibly elevated degrees of volcanic activity. Moreover, researchers may track down irregularities or surprising varieties in the spectra utilizing near spectroscopy. These abnormalities could address unmistakable elements of a specific exoplanet, suggesting the presence of particular climatic circumstances or maybe outsider life forms that go against existing speculations. It's like finding vast shocks and going beyond the domain of what we recently accepted was plausible. A more far-reaching comprehension of the tenability of exoplanets generally is additionally presented by near spectroscopy. Researchers can find out more about the different perspectives that lead to tenability by concentrating on a wide assortment of exoplanets. It supports our perception of the essentials for the beginning and upkeep of life in an assortment of enormous settings. According to NASA, Proxima B, which is just 4.24 light-years far off from our nearby planet group, has gained huge consideration because of its conceivable tenability. Life might be found there by the James Webb Telescope. Proxima B spins around Proxima Centauri, the parent star of Proxima B, a red dwarf that is still essentially more modest and colder than our Sun. This exoplanet was discovered in 2016 and is arranged in the Goldilocks zone, the star's habitable zone. The region surrounding a star known as the habitable zone is where conditions would be perfect for liquid water to exist on a planet's surface, which is fundamental for life as we know it. The finding of life on Proxima B is revolutionary in light of its closeness to Earth and situation in the habitable zone. Proxima B's potential to support life has produced a lot of consideration and speculation. It's memorable that an exoplanet's livability is a complicated puzzle with numerous factors to consider. With a mass of around 1.3 times that of Earth, Proxima B is classified as an exoplanet comparable to Earth. It takes it generally 11.2 Earth days to complete one circle around Proxima Centauri, as indicated by its orbital period. However, things are more muddled than they appear at first. It doesn't follow that the planet will be an indistinguishable copy of Earth and that anybody can without much of a stretch relocate there. In light of the fact that it circles a red dwarf star and is generally the size of Earth, there are different models that decide Proxima B's tenability. The atmosphere is one significant factor in addition to serving as a barrier against harmful environments. Atmospheres are fundamental for keeping up with life and controlling temperature. Still, the exact cosmetics of Proxima B's climate is not yet clear, which makes it challenging to make a firm assurance about its livability. Scientists are utilizing the James Webb Space Telescope among other instruments to examine Proxima B's climate. They can explore the light that travels through the exoplanet's atmosphere as a result. By inspecting the range fingerprints, researchers can look for intensifies that may be biomarkers, marks that highlight the presence of life. The presence of water is another perspective that impacts livability. Proxima B is in the habitable zone. However, whether it has enough water on it to qualify as a planet need yet be resolved. One significant part of the riddle is water, whether it takes the state of lakes, waterways, or seas. Researchers search for proof of fluid water on the planet's surface since the presence of water is important to support organic processes and is regularly viewed as a significant mark of livability. They additionally consider the presence of water in different states like ice or vapor. Proxima B's tidally locked state moreover asks concerns about its conceivable livability and climate. To determine whether Proxima B's temperature is appropriate for supporting life, researchers should likewise investigate components like pressure, temperature, and land activity. Life can challenge under outrageous climate circumstances, for example, extreme intensity or freezing cold. Moreover, stability is fundamental since livability may be upset by customary seismic movement or volcanic ejections. However, not all stability is beneficial. Proxima B is tidally locked, implying that one side of the planet is constantly enlightened by the star while the other is continually dim. The tremendous contrasts in temperature and atmospheric elements that could arise from the sharp difference between the consistently brilliant and everlastingly obscured sides could have an influence on the world's tenability. One more significant component in the chase after habitable planets is chemistry. Researchers analyze the planet's synthetic cosmetics with an end goal to track down organic mixtures, amino acids, and different chemicals that act as the building blocks of life. Establishment for life researchers at long last ponder energy sources very much like we want our daily portion of caffeine. Life requires a jolt of energy. They are researching on the off chance that the planet's natural cycles are adequately controlled by energy from its star or other sources. The inestimable apparatus of life is moved by energy, which permits living things to multiply, extend, and prosper. However, does Proxima B genuinely meet the necessities to be alluded to as a planet supporting life? Is there genuine proof for it? The genuine finding of Proxima B was an astounding achievement. Proxima Centauri is our closest star neighbor. In 2016, space experts utilizing the high-precision radial velocity planet searcher HARPS hardware viewed as the weak gravitational pull of an exoplanet around it. The extremely exact spectrograph known as HARPS was made explicitly to find exoplanets, working out of Chile's La Silla Observatory. It has played a vital part in the finding of numerous exoplanets, including Proxima B. The Doppler spectroscopy method, generally alluded to as the radial velocity method, is the foundation upon which HARPS operates. By detecting the minute changes in the star's spectrum caused by a circling planet's gravitational attraction, it finds exoplanets. These changes, now and then alluded to as Doppler or radial velocity shifts, are brought about by the star's small wobble as its companion planet's gravitational pull pulls on it. Light from the objective star is gathered by the instrument's optical fiber and coordinated toward the spectrograph, where the light is separated into its constituent frequencies. This separation enables cosmologists to analyze the star's spectrum in perfect detail. In this way, the radial velocity of the star can be measured with remarkable accuracy. To achieve the serious level of exactness necessary for exoplanet location and to avoid the impact of thermal variations that could cause mistakes in the measurements, HARPS utilizes a temperature-controlled environment to stabilize the device. Moreover, it has an I-shell spectrograph with high resolution, which makes it possible to detect even minute Doppler changes. The capacity of HARPS to recognize radial velocity differences as small as a few meters per second is fundamental for finding planets the size of Earth. Proxima B was found on account of this astounding accuracy, which enables cosmologists to detect the weak gravitational draw that planets have on their host stars, even when the planets are not readily perceptible. HARPS has been applied to exoplanetary system characterization in addition to planet tracking. Space experts can learn significant insights about the masses, whimsies, and orbital characteristics of exoplanets that have been found, which advances our comprehension of the assortment and composition processes of extraterrestrial planetary systems. Researchers have utilized an assortment of observational techniques and tools to better understand Proxima B. As we've discussed, ground-based telescopes, such as HARPS, have been significant in recognizing the star's radial velocity, but that is not all. Moreover, space-based programs like Kepler and TESS have added to our comprehension of Proxima B by utilizing the transit method, which notices a star's light continuously diminishing when a planet passes before it. Researchers can determine the exoplanet's size, orbital period, and different properties by closely examining the data. The orbital elements and atmospheric states of Proxima B are a significant area of study. By combining transit observations with radial velocity data, researchers have assessed the planet's mass, size, and density. This information offers quick data on its organization and possible habitability. While evaluating Proxima B's host star, Proxima Centauri, stellar activity is pivotal to consider while determining if the exoplanet is potentially livable. Proxima Centauri is more dynamic than more gigantic and stable stars like our Sun. Since it is a red dwarf star, frequent flares are an eminent quality of stellar activity in red dwarfs. Unforeseen magnetic energy discharges known as flares cause strong eruptions of radiation crossing the electromagnetic spectrum, including ultraviolet and X-ray radiation. The energy of these flares can outperform that of the best flares of all time recorded on the Sun by large numbers of times. Flare activity may influence Proxima B in various ways. First, it might cause the planet's atmosphere to dissolve. Proxima B's upper atmosphere might interact with high-energy particles produced during flares, leading to a continuous loss of gas. The planet's habitability might be straightforwardly affected by this atmospheric degradation because life relies upon a steady environment to exist and be safeguarded. Second, Proxima B's surface circumstances might be influenced by flares. Strong radiation, higher than normal UV and X-ray levels, has the capacity to go through the planet's atmosphere and reach the surface, where they might jeopardize life as far as we might be concerned. Radiation damages DNA and other organic molecules. Delayed high radiation exposure can be destructive to the growth and maintenance of complex living structures. Moreover, the energy that Proxima Centauri's frequent flares store into the planet's atmosphere can change temperature distributions, disturb atmospheric conditions, and affect the planet's overall atmospheric stability. These impacts could potentially affect Proxima B's current environment and atmosphere. The development of life and the persistence of stable ecosystems may both be compromised by these atmospheric fluctuations. Proxima B, however, is one of the best candidates in history to truly support the hypothesis of extraterrestrial life, even considering all that has been mentioned above. However, it is not the only event to celebrate over this finding. The quest for life on Proxima B or some other exoplanet is equally significantly impacted. The primary point is that it is formal proof that life exists somewhere else other than Earth. It would support the thought that life could exist in abundance throughout the universe, by offering solid verification that life is a real consequence of the conditions present in the universe. Researchers could learn significant lessons about the variety, development, and origins of life in the universe by investigating life on Proxima B with instruments more advanced than the James Webb Space Telescope. It would empower us to examine the assortment of potential habitats for life and perhaps reveal different biochemistries and unusual variations that exist beyond Earth. Further exploration would be important to fully comprehend these possible outcomes. Established researchers may be focused only on searching for livable exoplanets for impending space exploration projects, both within the Proxima Centauri system and in other nearby star systems. In addition to dedicated missions to Proxima B, because sometimes a breakthrough like this is just a positive development, there's no chance of understanding what wonders and opportunities look for you once you open them. Is Proxima B prepared to get the official designation of a habitable planet? Let us know in the comments section below. If it's not too much trouble, hit approval if you partook in this video, and we'll see you in the next one.